So yesterday we talked about voltage. We said that voltage is measured in joules per coulomb. Today we want to look at some applications. Basically, if a charge is moved through a voltage, its energy will change. It will either gain or lose energy. Example 1 says this: find the final speed of an electron beam if it's accelerated by 125 volts. Now here we have what are called parallel plates. There's actually a part 2 to this unit that I'm not going to get to, where we look at parallel plates that are charged. Basically, we've hooked one metal plate up to a negative charge source, one metal plate up either to a positive charge source, or in this case it's just hooked up to the ground. That's why it's 0. But here's what I want you to notice. By charging these up, we have created what's called a potential difference, a difference in voltage. What's the difference? Looks like it's 125 volts or negative 125 volts, depending on which way you're traveling. If we put a negative charge right there, an electron, and you know that this plate is negatively charged and this plate is positively charged, which way will this move? To the right. I think of, if you're looking for a good analogy for voltage, Mud, my analogy for voltage, it's kind of like height. Moving this electron through 125 volts is sort of like lifting something up to 125 meters. You've given it, when you lift it up, gravitational potential energy. By putting this electron here, we gave it electric potential energy. When I let go of the tennis ball, it will fall, because it's got gravitational potential energy. When I let go of the electron, it will, in air quotes, fall to the right because it's got electric potential energy. And what I really want you to notice is this is actually conservation of energy. Now, how do I know that? Taryn, what did they ask me to find? The final what? Speed or velocity? Speed. They didn't say how much work or anything like that. So we're going to write down KE initial plus PE initial equals KE final plus PE final. Taryn, what does it say that VI is? So you know what? We're starting at rest. We don't have to. We could actually have it already have some velocity. We would have cut a small slit right there for it to go through, and it would pick up even more speed. And remember I said this was the ground because it's 0 charge? You can treat that as the ground as though it's a height of 0. You can say once it leaves there, it's used up all of the stored energy. In the same way, when an object hits the ground, it's used up all of its potential energy. So what are we going to get for an actual equation? Well, kinetic energy is still a half mv squared. I guess this would be Vf. What about potential energy? Is this gravitational potential energy? No, this is electric potential energy. Now, we have a couple of ways to do that. Don't write this down. One way would be to go, well, K Q1 Q2 over R squared. Do you see two charges in this question? Xavier, there's another equation that has potential energy in it.
V equals PE over Q.
Get the PE by itself. Write this down. This is a little bit tricky because this is an equation that has an uppercase V and a lowercase v in it. This, Zach, is why my prof always put the wings on the capital V for voltage, because otherwise you might be tempted to cancel the V and the V out, because especially if you don't have lined paper, it's tough to see when something is capitalized and when it's not. But what we're really saying, in the same way as when you lift an object, you give it potential energy, mgh, and then when you let it go, that potential energy is turned into kinetic. When you move an object through a voltage, before we got here, someone must have, in air quotes, lifted the electron to the left because it didn't want to go that way because Taryn liked charges. So the electron didn't want to go to this negative charged object. And then held it there, held it there, held it there, let it go, and it falls. The only difference is you can kind of imagine instead of coming to a stop, we've dug a tunnel, it's going to keep falling, but the analogy breaks down because the tunnel, the object, if it was gravity, would keep accelerating. Here, it's not. There's no more acceleration. There's no more source of energy. What did this want me to get by itself? Oh. Times by 2, divide by little m, square root. 2q v divided by little m square root. Let's see. 2q, it's an electron. It's 1.6 times 10 to the negative 19. It's technically negative now. Are we inside a square root right now? Keep everything positive. Because you can also, the voltage is sort of, you know what, it's 125 volts and it's a charge of 1.6 times 10 to the negative 19. This is the one time when we're doing energy where we're not going to include the sign. Voltage, 125. All over the mass of an electron. Should be a fairly good speed. This is the beginning of how we set up particle accelerators, by the way. This is how we can accelerate protons. We would do this with a positive charge instead of a negative plate, and electrons. And we can pretty accurately control how fast we have them leaving this, I'll call it, electron gun. You want it to go faster? Bump up the voltage. You want it to go slower? Reduce the voltage. What do you get? Worth, by the way, I like this question, I like this question, I like this question. Worth also practicing typing it on your calculator because there's lots of scientific notation and square roots and things. .63 times 10 to the 6th. If you go scientific notation, sure. Go to the next line, Mr. Duke. You got room. Pretty fast. Fast enough that it's not like your eyes could detect the motion. It would just be a blur. By the way, what if instead of having negative 125 and 0, don't write this down, what if I had 0 and positive 125? Same effect, because like charges repel, unlike charges attract, it will be attracted to the right because of the positively charged, and it's still going through a change in voltage, a potential difference of 125 volts. Or we could have set this up for some strange reason with negative 25 and positive 100. That's still going to behave exactly the same way. It's going to be repelled by the negative while simultaneously being attracted by the positive. You're good. One of the things I haven't taught you, but one of the really nice things about parallel plates is electric fields between parallel plates are constant, which means the force is constant, and so we can use some shortcuts. So, as we see in the above equation, when a particle is accelerated from rest by a voltage, we have a pretty simple equation. All of the electric potential energy is turned into kinetic energy. You do have to be careful not to confuse V with V. Big V voltage, little v speed. And so we have this. QV equals a half mv squared. Really, it's a potential difference. And really, it's going to be the absolute value of that, because if you're taking the square root, you want it to be positive. What if the electron is already moving or the proton is already moving? Okay, an electron already moving at 5 times 10 to the 5th. Did I go too fast? Good morning, good morning. So glad you made it here. So an electron already moving at 5 times 10 to the 5th enters a setup. We call these accelerating plates. So here, this is positive, but this is even more positive. It's going to get pulled to the right. It's going to feel a force accelerating it to the right. Find its speed when it leaves the plates. Okay. George, what does it want me to find? Again, I'm going to argue that you can treat this change in, by the way, what is the potential difference? What is the change in voltage? 500. You can treat that like height, except I guess now instead of dropping an object, we're throwing it, we're giving it some initial kinetic energy. And I'm trying to give you a real-life physical analogy because voltage to me is so abstract, I really have a tough time wrapping my brain around it. So I think of voltage as height. And that works most of the time as a pretty good analogy. So I'm going to argue again, this is a job for conservation of energy. Are any of these zero? Well, the only one that's going to be zero is that one, because again, we'll pretend that that's the ground, that's the height of zero. Once it exits the plates, it has no more source of energy, and so it's not going to speed up or slow down. But otherwise now, this is going to be really similar to stuff we've done. We're still going to have kinetic energy being a half mv initial squared plus, qv, not mgh, equals a half mv final squared. Nothing really cancels. No m's cancel. I could, I guess, multiply everything by 2. You know, this is about where my love for getting stuff by itself ends. Sarah, I'm going to crunch this whole left-hand side, get a number, and then all times by 2 divide by m square root. So I'm just going to start to plug in numbers. Let's see, it's going to be 0.5 m. It's an electron. It was 9.11 times 10 to the negative, what? 31. V initial, don't forget the squared, 5 times 10 to the 5th squared. Plus Q. It's an electron, but we're not going to put the sign positive or negative in. It's going to be 1.6 times 10 to the negative 19. And the voltage, 600? How high did we start? 100. How high did we end? 600. What did we travel through? How much? This is why they often call it a potential difference. The change in voltage. This is why technically this is always a change in technically. And so we would say it's traveled through 500 volts. That equals 0.5 mv squared, or a half mv squared. Let's crunch the left-hand side. 0.5 times 9.11 times 10 to negative 31 times 5 times 10 to the 5th, don't forget the squared, plus 1.6 times 10 to negative 19 times 500 volts. I get a left-hand side working out to 8.011 times 10 to negative 17. Is that matching yours? I'll store this on my calculator. I'll write 8.011. Okay. 8.011 times 10 to the negative 17. That equals a half mv squared. And now I'm on familiar territory. I'm going to times by 2. Divide by the mass, which was, I think, 9.11 times 10 to the negative 31. Square root. That's going to give me the final speed. So 2 times answer button divided by 9.11 times 10 to the negative 31. Square root of that. And I get 1.33 times 10 to the 1, 2, 3, 4, 5, 6, 7. 1.33 times 10 to the 7th meters per second. That makes sense to me because I know the electron sped up. Oh, what would happen, look up for a second, I'll scroll back down. What would happen if this was not 100 volts, but positive 1000 volts? If this side was more positive than this side, the electron wouldn't speed up. What would it do? Slow down. We can do that too. We can pretty much fine-tune the speed of a particle using this method. Get it very accurate. Example 3. That work okay, Paige? Yeah, no, or yeah.
No.
Okay. We'll look at it later in the typing. Remember gravitational field, we said had 2 units. It was meters per second squared, which is what we used last year all the time. It's the acceleration due to gravity. But it was also newtons per coulomb newtons per kilogram if you just thought about F equals what M, you get the A by itself. It's got to be newtons per kilogram. Electric field, I told you, also had 2 units. The original was its definition, newtons per coulomb. But it says, prove that another unit for measuring electric field is volts per meter. In other words, prove that volts per meter is also newtons per coulomb. I can do that. Yeah, I can do that. Volts per meter. What was a volt defined as from that little energy equation that you read to me? It must be joules per. Okay, so I can write this as joules per coulomb per meter. Joules is a measure of what? Energy. Work. What was our original basic, not as useful definition of work, but the one that we started out with? Work equals what? Okay, so a joule must be a Newton meter per coulomb per meter. I got a meter on top. I got meter on the bottom. Oh, what's left behind? Newtons per coulomb. Volts per meter and newtons per coulomb. It turns out those are both ways to measure electric field. So if I scroll back, the reason this electron is accelerating, it must be experiencing a force. If it's experiencing a force, that must be because there's an electric field acting on it, because that's what causes charges to accelerate, the same way gravitational fields cause masses to accelerate. Oh yeah, and you can measure the electric field. That's why they gave you this distance. I stole this from a different picture. You could actually calculate the electric field. It would be volts, 500, divided by 0.01. This has an electric field of 5,000 newtons per coulomb. And it's a much nicer way to calculate electric field than going KQ over R squared, and it's cleaner. So, how does an older TV work? By an older TV, you may still have had those when you were growing up. A TV that had that big thing jutting out the back. Or you might have seen a computer monitor that had that jutting out the back. Or we may still have some in our school that have those older computer monitors. We've gone to flat screen mostly, and flat screen technology, totally different. I love flat screen. I do. But I miss these because I could explain to my students how their television was working. So this is only about 10 years out of date. At the heart of every old TV was a cathode ray tube. There was a tube back here, an electron gun. Except the first person to invent this didn't realize that they were electrons. He called it a cathode ray. We now know that they're electrons. Abbreviation for a cathode ray tube, a CRT. These used to be called CRT screens. So a CRT is a cathode ray tube, an electron gun. In the simplest cathode ray tube, a beam of electrons is accelerated by one set of plates, then deflected by another. It hits a fluorescent screen which glows. So here is how a black and white television would work. And then we'll talk about color. They would have a glass screen, and they would have painted the inside of it with a phosphorescent paint, a paint that if you hit it with an electron would very briefly glow. That's step one. Let's zoom in. Don't write all this down. We'll do a neater version in a second, but I'm really going to muck this up. First thing that we would do is we would charge this very negative so that electrons would just bleed off into the air. I didn't include it in the diagram, but we would also put a negative plate right here and a negative plate right here so that it would push all the electrons towards the middle and you would get a nice straight beam because like charges. Okay, get rid of those. We can control the speed of this electron with great accuracy. We just noticed that. So we would send an electron out, and here it would come to deflecting plates. We would actually have two sets of deflecting plates. This set of deflecting plates is deflecting the electron beam up and down, but we'd also have another set of plates angled vertically to us, and that would deflect the electron left and right. We'll look at that a bit more. So as the electron, if this is positive and this is negative, which way will the electron get deflected? Up or down? Okay. And we would make that dot glow. Oh, bump up this voltage. Now you'll make that dot glow. Flip the voltage. Reverse it. You can make that. You can make any dot you want to glow. And add a second set of plates that can deflect it left, right. You can make any dot you want to glow. If you're clever, you can make them glow to form a picture. And you can rewrite that picture 60 times a second, and your brain will translate that into moving pictures. This is how television worked. I used to ask this as test questions. I'm not. This is purely for nerd trivia. So put your pencils down and look up. Here is a cartoon from the 1950s, but it does a great explanation of explaining how a cathode ray tube television system works. Where is Professor Whoopi? Where is Professor? There he is.
But there's still something I don't understand, Mr. Whoopi.
Well, what's that, my boy?
I looked real close, and I didn't see any picture going across the room between the camera and the TV set.
But of course you didn't. There wasn't any picture, just electromagnetic waves which are invisible.
But then how...
How does it get to be a picture again? Well, let's go back to the 3D TV. Inside every TV set, there's a big tube. You call it a picture tube, but the correct name is cathode ray tube. It takes the waves from the transmitter and turns them back into electrons. In the back of this tube, there's an electron gun which shoots the electrons at the front of the tube. The front of the tube is coated with a special chemical which lights up when the electrons hit it. And this is what makes the picture.
I get it. The Autocon tube turns the picture into electrons.
So the Autocon tube, that was the original television camera. That would take an image and turn it into an electrical signal. And you would just send that electrical signal to an electron, to a TV, and boom, you would get the image. You didn't have to do any translation. It was analog technology, not digital. It was one-to-one. It was very simple. It took care of all the voltages itself. It was really, really simple and straightforward. Didn't get a great picture, and it was subject to interference and static and all that stuff, which is why we moved to digital, but really basic technology.
And the cathode ray tube turns the electrons back into the picture.
Precisely, my boy.
That's black and white TV. How do we do color TV? Well, we have 3 tubes originally. 3 tubes, each one doing a different color, and then your eyes blend those colors into all the colors of the rainbow.
How does the monitor work? Signals from your computer's video card are loaded into 3 electron guns at the base of the monitor. There is one gun for each of 3 colors: red, blue, and green. These 3 colors, when mixed together, can create all the colors you see on your screen. Now, these guns don't shoot bullets. Instead, they shoot a powerful beam of electrons towards the face of the monitor. The beams pass through the deflection yoke. It uses magnetism to bend the electronic beams so they can sweep across the entire screen and...
So there's a bit of a lie there. We now use magnets to bend the beams instead of plates because that allowed us to make the TVs smaller. The plates had to be physically long, parallel plates. Those took up room. Turns out you can also bend electrons with magnets, and you can make the magnet significantly smaller, and so the back of the TV can be jutting out even shorter, smaller, better.
Create the picture we see.
What happens once the beams have swept your monitor? Special chemical phosphors are painted on the inside of the monitor. Energy from the electron beams makes the individual phosphors glow either red, blue, or green, depending on the type of phosphor. The stronger the electron beam, the brighter the phosphors glow. A sheet of metal with holes in it helps keep the electron beams aligned exactly with the phosphors. This is called a shadow mask. The beams sweep across the entire screen 60 times per second.
What were the 3 colors that they were using? Did you notice? Okay, that's the original RGB monitors that were very, very popular. Again, we've moved well beyond that, but 10 years ago, this was still, 15 years ago, this was still fairly relevant.
It happened so quickly that you are unaware of the firing process. Instead, your screen appears to be a steady, continuous image, just as it does now.
Okay, but really, it's painting an image 60 times a second. So, example 5. Now we'll start to draw. Below is a side view of a very basic CRT and a front view of the CRT screen. The electron beam right now is hitting the middle of the screen. You probably have never seen it, but old-style TVs, when you turned them on, they had to warm up. And at the beginning, you would just see a bright dot dead center. That was the electron beam coming straight out of the page at you. In fact, what you used to be able to do with TV screens is if you put a piece of tin foil right onto the TV screen, and then you clipped an alligator clamp on either side, you could get current from there. You could actually run a small little tiny device from there. There's enough electrons, you would actually get a small moving current. Not big, but you could do some nice little static electricity stuff with it. Okay? So, right now, the electron is hitting dead center. We have 2 sets of plates, deflecting plates. We have a Y plate. That's going to deflect this up or down, depending on whether we make this one positive or this one's positive. And then we have the X plates. That's going to deflect it left and right horizontally, depending on whether we make the far plate positive or the left plate positive. So here's our thought puzzles. I want you to imagine that you're the person sitting in a chair right there looking at the screen. So this is your view. Where will the electron dot end up? Choose from location A, B, C, D, or E in this little picture below. Originally, we're starting right here. If we make the upper deflecting plate positive, so if we make this plate positive, where will the electron end up? A, B, C, D, or E? I think A, if we make, don't write this down, if I make that positive, the electron's going to get bent this way. Yes? Because unlike charges attract.
Well, I thought it would like deflect off.
No. If it's positive, it's going to get pulled towards it. Deflecting just means we're changing the angle. You don't have to think repelling. It could be attracting as well.
So it doesn't actually hit the plate?
No.
Oh.
No, we just bend it in between them. We want it to hit here. If it hits the plate, we don't get that little phosphorescent blink glow over here. So, A, is that okay? Make sense? What if we make the right plate, so back to 0, so we're hitting dead center. What if we make the right plate positive? Will the electron hit location A, B, C, D, or E if you're sitting in that chair looking at the screen? I think if we make this plate positive, I think the electron's going to get bent that way. Yes? From our viewpoint. So I think it's going to hit B. You got to kind of imagine where you're sitting, right? What if we make both the upper and the right plate positive? So you're starting to see how with basic analog technology, we could make any dot that we wanted to glow. We're very close to inventing television. Let's kick it up a notch. I think I got one more. Suppose we adjust the voltage so that originally the electron beam is hitting a point above dead center before we even turn the deflection plates on. It's just coming out a little faster. It's hitting a point above dead center. Where will the electron dot end up? Choose A, B, C, D, E, F, or G if we increase the deflecting voltage. So right now it's being deflected a little bit. What if we bump up the deflecting voltage? Will that deflect it more or deflect it less? So, what letter? G. Okay. What if I put it back to here, but now I reverse the polarity of the deflecting voltage. So now the bottom is positive, top is negative, but same magnitudes. See? Ooh. What if I increase the accelerating voltage? What if I have it leave the electron gun faster? If it's traveling faster, will it be between the plates longer or shorter? Will it get deflected more or less? So? And my point here is you can see we've got complete control. We can put this little dot pretty much anywhere we want. The rest of the advances in technology of television before we went to the flat screen technology, it was just getting better and better accuracy so that you could get a better and better picture, but it wasn't changing the concept of the technology per se. It says explain your answer using principles of physics like we have. So example 9. How does our simple model of a cathode ray tube, a CRT, explain how a black and white TV works? Only one dot or pixel is hit at a time. Typically, the way old school black and white televisions worked is we swept the Y voltage from negative to positive. What would happen is the beam would go like this, far quicker than your eye could see, but you would paint it up and down, and each time you would just step the horizontal voltage deflection up by one again, up by one again. And that way you could slowly move the beam across the screen while painting an image. Then when you got here, you would just reverse it, and 60 times a second, your brain would meld the images perfectly. Okay? You may have seen old movies. I'll ask, have any of you ever used a black and white TV? One, okay, two, couple. Like I actually had one briefly growing up. We got color when I was about 5, but we still had an old black and white. That's the dials and the knobs where you were adjusting the image. What you were really doing is you were literally fine-tuning these. You were moving the plates or the accelerating plates around ever so slightly because there was, if there's more static in the air, that's going to change the image ever so slightly. You got to do a little bit of adjustment. It's more humid. It's dry. There was all sorts of factors at play. Temperature could change things. So, okay. So basically, we step the beam over using a small change in the X voltage. So it would go, there's the first dot right there. Boom, boom. Bump up the X voltage again. Boom. Bump up the X voltage again. Boom. Bump up the X voltage again. Boom, 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 boom. And you can see you would get all the way across. So if we gradually add increments of X voltage while sweeping vertically, we illuminate the entire screen. The TV signal turns the cathode ray beam on and off as it sweeps the screen. So beam on is a white dot. Beam off is a black dot. Beam partially on, gray. And that's how you got the 3 shades for a black and white TV. Then when we went to 3 electron guns, we got color TV. Okay. I can remember growing up, hotels would be advertising color TV on their banner. I don't think they bother doing that anymore. They always advertised color TV. The word color was in color, in the colors of the rainbow. Like, look, we've got color. That's a big deal. Okay? Yes, I'm that old. Put your pencils down, look up. You were talking a while ago about a Faraday cage. There's also something called a Faraday suit. This is a suit that's basically got metal woven in it. And if you're wearing it, you can be around electricity and be completely safe. How many of you have seen the massive power lines, the ones that go over the mountains that are on the big metal towers, those ones? Okay. How do they repair those? Because those go across the country, and in many places, there's no road access to repair them. Well, they do this. Put your pencils down, look up.
And empowers this white knight on a quest to keep the juice flowing.
I don't give two hoots and a holler about flying inside a helicopter. Put me outside. That's where I would be. On the magic carpet. Back in the late 1800s, there was a gentleman by the name of Michael Faraday. He had a theory that if you enclosed a man in a metal cage and energized that cage at whatever voltage, the man would still live. The voltage would flow around him.
So they're bringing the helicopter and the man to the same voltage potential as the wire. Basically, if we go back to my height analogy, they're bringing everything to the same height. If everything is level, if you're on a level floor, will a ball move? If you're at the same voltage potential, will charges flow? No.
I wear a hot suit. It's 75% Novex for fire retardant and 25% stainless steel thread. And that metal thread means I have a Faraday cage around me. 500,000 volts pass over my body, but I can work without interference from the electricity. As long as the helicopter is isolated from the ground, we have the ability to bring ourselves to the same voltage potential as the line. Like a bird on a wire. Our pilots are very smooth. It's like they can read our every thought.
So that's a job. If you're looking for probably a fairly interesting job, I don't know, and you clearly can't be scared of heights.
There's such a hunger for electricity these days. Nobody wants to take lines out of service just to maintain them. I've had many people ask me, do you know what you do is safe? And I say, well, in our operation, everything that we do, every move that we make is thought of and rehearsed before. So it's as safe as crossing the street. It's not a job for a hot dog. There's only three things I've ever been afraid of. Electricity, heights, and women. And I'm married too.
So there's your Faraday suit. Absolutely works. What's your homework? Number 1 is good. Number 2 is good. Number 3 is good. Number 4 is good. You can skip 5, 6, 7, 8, 9, 10. 11 is good. 12 is good. 13, and 14. That's basically 11, 12, 13, and 14 are pretty much, this is what you can do with point charges. You can find the force between them. You can find the overlapping electric field between them. You can find the potential energy between them, or you can find the overlapping voltage between them. It's a good summary of everything. Basically, we're done the unit. Tomorrow I'm going to talk about lightning and give you a take-home quiz. So you can also now technically do every question on the ultimate review.